Okay, hi everyone. Boy, we are sparse today. Let's start recording.
Hey, can we have like more classes today?
It's like 20, 25 people. So we're at like 2/7 of our one number. I guess I hear people are reeling from a machine learning prelim. So maybe that's what's going on. We can take a nap. We will, maybe this is a little bit of a signal that it's time to start transitioning to more lab as opposed to lecture. So let's start thinking, let's do that maybe next week. I think we'll meet on Monday because I want to, as final project proposals come in, there are a few topics that will be relevant for a few projects that I want to just go over. But then beyond that, I think we'll transition to more lab time. Maybe I told you last time, I reserved the 2:38 lab. So we have afternoon labs on Wednesday, Thursday, and Friday from 1:30 to 4:30. And I extended that reservation so that it begins at 12:30. So on Monday, no, I'm sorry. On Wednesday, Thursday, and Friday, from 12:30 to 4:30, I'll be in the lab and the lab will be open. Starting whenever we do this transition. 2300 is in the lab for this time on Mondays, but I'll be in there from 3 to 6 on Mondays. So what that means is there should at least be 2 extra hours that fit into everyone's schedule of lab time per week because they're in these lecture times. So any questions from anyone? Okay, there were a couple of things I wanted to just go over quickly in connection to lab 3. Overall, I would say lab 3, it appears as if there was a lot of initial bugs associated with lab 3, but people, once they get over those initial bugs and get the thing moving, things are going relatively smoothly. In a number of groups with some pretty well-tuned. I do just want to remind folks so for the week 3 checkout, what do we expect? The notion is that you will have, let's see, how to explain this. So you will have a device that when you turn it on, so at reset, the device will execute a maneuver. So it turns on, it goes up to 90, stays there for about 5 seconds, plus 30, minus 30, back to 90. And then it just sits there at 90. And you as the user can then specify a new angle that you would like for it to assume. And then it'll go there, it'll go there, it'll go there. And then by some mechanism, it could be a button in the GUI, it could be a physical button, whatever you want. When you push that button, I would like for the maneuver to be executed again. And then part of your deliverable for the lab report will be the scope traces of your potentiometer readings through that maneuver and the associated control input throughout that maneuver. Okay. And that interface should also allow for you to be able to change the PID control parameters dynamically. So you change it and it instantly takes effect. I talked last time or a few times ago about how I would like for when the user enters a new angle, I would like for the user to be able to enter, if it's currently hanging at 90, the user should be able to enter 90 and the new desired angle immediately becomes 90. As opposed to implementing this in something like a slider, where as you slide it up, the desired angle becomes 0, then 1, 2, 3, 4, 5, 6, and counts up quite quickly to 90. That just gives the arm slightly different behavior. And I'm interested in the step response. So when you say go to 90 degrees or 0 degrees, however, horizontal, I'm interested in seeing what it does. So a strategy that I've seen a lot of groups use to do that is to implement a slider for setting the desired angle and a send button, so that you can use the slider to set the angle, but then that angle won't actually be sent to the device until send is pushed. That works pretty well. I've seen a few other groups use text input. That's also fine. I just ask that whatever you decide to do for that desired angle setting, allow for the user to instantly specify a new angle that's greater than 1 degree away from the old angle. If that makes sense. Any questions about deliverables? So I've seen a bunch of proportional controllers that look quite good. I'll just remind you of the strategy here. So you will start with proportional control with a quite low proportional gain. And what you'll see is when it's quite low and you command 90 degrees, the motor will weakly turn on and stop maybe here. And you'll turn it up further and further, and eventually you'll find the point where it starts to oscillate. And that should attenuate the oscillations and have it settle out. And then to make up for the steady state area, you'll add integral gain. And then you'll start tuning, right? And you can start playing this game where you think, well, I would like for the system to get up faster, so you'll increase proportional gain. And as you do that, you'll see greater overshoot, so you'll turn up the derivative gain a bit more. And you'll find some set of parameters that you like, that gives you a response that you like. When you find those parameters, make them your default ones, so that at startup, the controller has those gain settings, but then the user can change them as you desire. Okay? It's pretty satisfying once it starts working. I've seen a lot of groups playing with this, where you push it down and it yells at you, it starts to come back up. So I wanted to, unless there are questions about Lab 3 expectations, I wanted to just wrap up our slightly more analytical discussion of what's actually going on as you change these PID control parameters. And I'll just briefly remind you that what we did last time is we were looking at the physics involved in this system, specifically the motor physics, the motor being a thing that takes voltage as an input and gives you propeller rate as an output. We looked at the transfer function associated with that. And then the pendulum physics, which takes motor propeller rate as an input. In our analysis, we just treated it as thrust as a, or I'm sorry, yeah, we treated it as a thrust as an input, and as an output gives you an arm position or an arm rate. And we were looking at these two transfer functions. One of the things that so in order to do this, we came up with a set of differential equations for the motor. One of those differential equations modeled the motor as an electrical system. The other modeled the motor as a mechanical system. And we made some substitutions and put these two differential equations together to come up with a transfer function that transfers voltage as an input to propeller rate as an output. And what we saw, which was hopefully not surprising to anyone, is that the Bode plot for the motor looked a lot like a low-pass filter, right? It passes low frequency, and then once you get up to high frequency, it starts to attenuate. And we made the observation that as compared to the physics for the pendulum, the phase change associated with the motor was at quite high frequencies, which means that it's the pendulum physics that's really driving our controller design, the stuff that's happening at lower frequencies. So we then looked at the pendulum physics and did a really similar analysis, which is to say we ended up with a differential equations. It was a different set of differential equations, but okay, it's just a set of differential equations. And as before, we Laplace transformed them to come up with a transfer function, this one being a transfer function that transfers thrust to arm angle. And we looked at the Bode plot for this. And what we saw was something that looked like this. We saw the amplitude part of the Bode plot. We saw a resonant peak right where we expected for it to be at about the square root of 9.8 over the arm length, which you'll remember from physics 1112 or something. And then we noticed that after that resonant peak, the amplitude response rolled off at minus 40 dBs per decade. And we remembered from, I don't know what class, that at that resonant peak, we expect a phase shift of about 90 degrees. And at high frequencies, a phase shift that's approaching 180 degrees. If we were to include the motor in this as well, have a transfer function that goes from voltage all the way to arm angle. So, voltage to propeller rate to arm angle. What we would see is that at high frequencies, we would also see the phase contribution from the motor, which would cause this to roll off well below 180 degrees. And we were looking at this Bode plot to try to make sense of the phenomena that we were seeing when we were changing these PID gains. What we were trying to justify that in terms of the Bode plot. So one of the things that we were noticing, one of the things that you notice when you're starting to tune your PID controller is you start with proportional gain. Okay, so we're looking at Bode plots like this, and as you add proportional gain, the effect of that is you are raising the amplitude response and not affecting at all the phase response here. So just to illustrate this, you can see that as currently set up, this amplitude response starts at about 0 dB and then peaks at a little above 10 and then rolls off. Suppose we were to add a little bit of proportional gain. What we might see instead is an amplitude response that looks maybe like this, where it peaks a bit higher, right, and then rolls off. And what we were noticing is we were keeping an eye on the phase margin here. So we were remembering that the conditions for instability, as illustrated on a Bode plot, are if our Bode plot ever achieves minus 180 degrees of phase shift at greater than 0 dBs of gain. What that means is, what's minus 180 degrees of phase shift mean? It means that in our feedback system up here, we have some input. 180 degrees of phase shift means a sign change on the output. This becomes positive feedback, and the whole thing starts to oscillate with increasing amplitude, right? It's unstable. So that's the condition of instability as observed on the Bode plot. It's 0 dBs of gain at 180 degrees of phase shift. And we measure how stable a system is in terms of gain margin and phase margin. And to get a sense of these things, what we would do is, let's put this back down to about where it was. What we would do is look at where this crosses 0 dBs, which is about there, and then look at the phase that we've got at 0 dBs of gain. Right now it's at, I don't know, maybe like minus 135 degrees of phase or something. So what that means is that we have 180 minus 135 degrees of phase margin. We could add that much more phase to the system before it would go unstable, right? It's a measure of how stable or unstable our system is. How much phase margin do we have? At the 0 dB crossing point, how far away are we from minus 180 degrees of phase? We speed our system up by adding proportional gain, right? The amplitude response is increasing, but as we're doing that, something else is happening. As we're doing that, the other thing that's happening is this 0 dB crossing point is moving out, which means now we have significantly decreased phase margin. The amount of stability in our system has decreased, which means adding just a little bit more phase will make the system go unstable. And even in this point, what you can expect is tons of oscillation. So this is why, this is the explanation for the effect that you see, where as you turn up proportional gain, the system gets faster, but it also gets increasingly unstable. It starts to oscillate, and then you turn it up more and it oscillates more. And eventually you may find a point where it starts to oscillate out of control. And that's because there's some phase being introduced into the system that maybe we aren't modeling that's driving the system to instability. What could introduce additional phase into a control loop? There are a few things. A big one is delay. If there is a delay between your control input and when that control input takes effect, that is phase. That shows up as a decrease in phase here. So delay in your control system can drive it to instability. I had a friend who was working on this project where, have you ever watched birds approach a power line and they kind of arch up and then land on the power line? They were trying to recreate that effect with autonomous little aircraft. They wanted to be able to throw an aircraft at a power line or a string and have it perch and then like charge itself, right? Really hard control problem because there's a lot of crazy stuff that happens there. He had, so it was an RC plane, and he was doing his control input via a hacked RC controller. There were a handful of milliseconds delay associated with that whole thing. It was enough to destabilize everything, right? Very, very sensitive system. So a little bit of delay in your system adds phase and can destabilize. But we want our system to be fast, right? So how do we combat against this? So what we want to do is to be able to increase this proportional gain, which is going to increase the speed of the system. But we want to do something to fight back against this decreased phase at high frequency. How do we do that? With the derivative control, the derivative term in the PID controller. What a pure derivative does is add 90 degrees of phase. And exactly where that 90 degrees of phase starts getting added depends on the value of that derivative gain, right? So let's see if I can do this in real time. Let's look at the Bode plot for a PD controller. So let's call this system 3, and our transfer function is just going to be, oh boy, can I do this in real time? It's going to be KP, it's going to be KD plus, it's going to be KD, KP, and nothing in the, and 1 in the denominator, I believe. I might be screwing this up. If so, that's okay. And I'm screwing this up. I can't do this in real time. That's okay. The point that I was going to make is if you look at the Bode response for a PD controller, what you'll see is in the phase part here, you'll see it's flat and then it goes up by 90 degrees. So what we do when we're adding the derivative part of the PD controller is a little bit after that resonant peak, and you determine this experimentally, you're starting to add phase back so that we're still getting the fast response associated with a high proportional gain, but we are preventing the phase margin from decreasing too much, which is adding back stability. Now you add too much, you slow the system way down, right? So these are knobs that you turn. More derivative gain, faster, less stable. I'm sorry, more proportional gain, faster, less stable, more derivative gain, slower, and more stable. And then we add a little bit of integral. What does the phase plot of a pure integrator look like? Don't remember. Kind of an obscure question. That removes phase, that subtracts phase. So we need to be careful with that integral term, because if we're not careful, it will decrease the phase even further and destabilize our system. So a little bit of it brings it up to the desired hover angle. Add too much, and what you will see is instability. So this is sort of the balancing act that we're doing. And a lot of this discovering is sort of, in our case, done experimentally. There are systematic ways to go about getting good estimates for these controller gains. In our case and for our system, we start with reasonable guesses for all of them. Well, we start with a reasonable guess for proportional, destabilize the system, stabilize it again with derivative, and then add just enough integral to get rid of the steady state error. Questions about this stuff? Okay. At this point then, the stuff that I'm going to start going over is things that I have seen in project proposals and that will be useful to some people doing those projects. If I see a topic that exists or is relevant for enough project proposals, it's the sort of stuff that's broadly relevant enough to go over in class. So there are a few of these things. So in no particular order, one of the things I feel like we should just talk a little bit about is stepper motors here, in contrast to the DC motors that we've been working with. Maybe work with stepper motors before. Yeah, okay. So they have a significantly different internal mechanism than the DC motors. So I'll just remind you what the internal mechanism of the DC motor looks like. We've talked about this quite a bit, but we apply DC current to the device here. And what we're looking at, play the animation, is there is a static magnetic field here with a loop of wire called the armature going through here. We apply DC current to this device, the commutator, which allows for the armature to rotate, but it maintains electrical connection so that the current can continue to flow as this thing rotates. And as the commutator rotates, in this illustration, it's divided into two parts so that every 180 degrees, the direction of current through the armature switches direction, so that the mu cross B torque is always in the same direction for this armature, right? So we put current through here. We have current through a loop of wire in a magnetic field, creates a torque. And then once it flips 180 degrees, in order to keep the torque going in the same direction, the commutator here flips the direction of current in the armature so that it continues to get torqued in the same direction. We change the direction of the motor by changing the polarity of the applied voltage to the commutator. So that's what a DC motor's internal mechanism is like. We talked about a lot of the consequences of this. One of the big ones being noise, right? The fast switching of current direction here is producing large DI/dt spikes, LDI/dt spikes, which we have to protect our circuit against, which is why you all built that motor control circuit that involved the optical isolator. A stepper motor's internal mechanism is different, and this is a highly simplified schematic of the internal mechanism of a stepper motor. What you have is, so sort of protruding out of the center of this magnet, you could imagine the actual armature of the motor that spins. And inside of a stepper motor, you have a series of electromagnets. In this illustration, I'm showing you.
I didn't get
You gotta
that.
turn that
Could
off.
you try again? Sorry, I can't do that.
You have, I'm not going to say the word, a collection of electromagnets. I'm only showing two here, but in reality, there's a whole lot so that you can get a whole bunch of different orientations of the internal permanent magnet. But the way that this works is, you could imagine if we applied current in a particular direction through this coil of wire wrapped around this electromagnet to induce a magnetic field in the core, and didn't apply it in this one, there would be one stable configuration for the permanent magnet would align itself with the magnetic field of the electromagnets, right? And then what we could do is stop applying current here, start applying it here, and it would pop into a new stable configuration. So you can imagine by playing with the polarity of this input, that input, and that input, you could get this thing to rotate. And in an actual stepper motor, this is showing you, we have 1, 2, 3, 4 stable configurations here. In an actual stepper motor, you'll have perhaps hundreds or thousands, right? So you can have really quite high fidelity control. So this is what's nice about this. One of the things that's nice about it is because of the way that this mechanism works, you can have quite accurate knowledge of the position of the motor without doing any feedback. If you're just counting the steps of the motor, then if you said, hey motor, go forward 5 steps, and you know where the motor started, you know where it is, right? Because it's in the stable configuration associated with step 5, which means you can do pretty accurate position control without the need for feedback, which is nice for some applications. The other thing that's nice about these is they are super high torque, and they have a super high holding torque. They're not as high speed as a DC motor. So you wouldn't probably want to use one of these to do something like run the wheels of an RC car. That kind of thing doesn't make sense. But if you wanted to, suppose you were building something like a plotter that was moving some pen over a piece of paper, where you cared about relatively accurate position controlling, and you wanted to be able to torque a mechanism pretty hard, a stepper motor probably makes sense for that. If you wanted to twiddle the knobs of an Etch-a-Sketch, a stepper motor probably makes sense for that. They tend to be a little bit more expensive, but that being said, let's see, I've been experimenting with stepper motors, the ULN2003s, which for a pack of 5, I think they were like $13. So they're not crazy. By the way, you get one of these things. It's pretty easy. The pinout for these is not always, if it's difficult to find the documentation, it's pretty easy to determine the pinout with a multimeter, right? You just take each of the leads and figure out which ones are the ones that are shorted, and you can pretty much deduce the internal schematic of the device. Anything else to say about this? So useful for position controlling, useful for really torquing things, and they have quite a nice holding torque. There are other flavors of motor. One that probably pretty much all of you have worked with, servos. A servo does have a little feedback control system in it. So an unmodified servo motor you use for position control, right? In some classes, you guys may have used modified ones where it spins continuously. But you can buy those actually, but you can also modify a normal servo to do that. In any case, inside of the servo motor, you are specifying a desired position of that motor encoded as the duty cycle of a pulse train that you send into the motor. That specifies the angle that you want. And then there is a feedback mechanism, a lot like the one that you guys are building in Lab 3 inside of the servo to steer it to the desired position. So we're measuring the current position of the motor by means of a potentiometer, looking at the error between the desired position and the measured position. That goes into a controller, which converts that error into a voltage that gets applied to an H bridge connected to a DC motor. And that DC motor then turns until that error is driven to 0. So inside of the servo, there is a DC motor. There's just a potentiometer and a controller that's controlling the voltage that's being applied to that DC motor so that it gets steered to the correct orientation and then stops there. So here's a exploded view of one of these things. There's a DC motor here. There's often a gearbox coming out of the DC motor. The output shaft is connected to a potentiometer to measure motor angle. This goes into a controller that's driving an H bridge that moves the DC motor. So if you wanted to modify one of these to be continuous rotation, what would you do? You would probably open this up and turn the potentiometer to the position associated with, if the servo can move from -180 to 180, you'd probably turn the potentiometer to the position associated with straight forward. And then you'd cut this line, or no, which line would you cut? You'd cut this line so that the potentiometer reading is always the same and pointed in the same direction. And then when you apply a desired position, the measurement is now never changing. So the motor just spin continuously to achieve the position that you commanded. And usually doing that, so that involves breaking these things apart, going in and turning that potentiometer to the desired angle. Usually there's a little thing you have to snip on the gearbox to allow for it to turn through a full rotation. And then you end up cutting one of the wires going into the controller for the servo. So a little bit of surgery, but it's not too difficult. So some of you might use DC motors in your project. Some of you might use servos. Some of you might use steppers. Any other actuators people think they might use? People heard of nitinol? This is a slightly more exotic one. Nitinol is it's a nickel titanium alloy. It looks a lot just like a wire, and it'll pass current kind of like a wire. It's a resistive wire. But it has this interesting property that when you heat it up, its length decreases by something like, is it 2%, I think? Which doesn't sound like a lot, except that it's really strong. So, you have some mass attached, is perhaps being held up by a string of nitinol. You heat up the nitinol either with a heat source or by passing current through it, and you can lift quite a heavy mass. The other interesting thing about them is they are what's called a shape memory alloy, which means you can take a piece of nitinol and, like a piece of wire, you bend it into some shape. And if you heat it up in that shape, it remembers the shape that it was in when you heated it up. So then it cools off, you scrunch it up into whatever shape you want. And when you heat it up again, either with a heat source or with current, it pops back into the shape that it had previously. Which just sends you down some interesting, what applications can you think of for that? So it's a programmable shape for wire. So the applications of that seem kind of cool. I like the idea of a spacecraft that has some certain shape, like a solar sail, that has nitinol sort of tendons, and then when it gets heated up at atmospheric reentry, it folds itself into an airplane. think that would be neat. Or you could, there's this whole field of study, foldable robotics, that makes use of these things, as far as I understand. Other actuators, just on the topic of actuators that you might use, solenoids. These are quite simple actuators, sort of technologically. It's a loop of wire with a core in the middle. You pass current through the loop, creates a magnetic field, pushes the core out or sucks it back in. So it's a very simple linear actuator. If you care about moving things quickly over short distances at like kilohertz rates, an audio speaker could be a little actuator for you. You attach something to an audio speaker and it'll oscillate it, right? I think Bruce did some project. He'll be back next week. You can ask him about it. I think he did some project where he was trying to simulate some species of spider taps on the ground territorially at a certain frequency, and he was trying to build like a fake spider to trick other spiders or something. A very Bruce thing to do. But I think he did that with an audio speaker. And then if you care about very high frequency actuation over very short distances, you might consider something like a piezo actuator. There was a student in this class, this is another one you can ask Bruce about when he's back, because this was before my time, who somehow, using piezo actuators, in this class for a final project, built a scanning tunneling microscope that worked. The student was able to image and move around gold atoms in a 4-week project, which is just insane. Okay. Other questions about this stuff? The other topic I wanted to cover, because there's a handful of groups that are doing projects that require orientation determination. So either of a controller or of an arm or something like that, where they care about the orientation of something in 3D space. And so I want to talk about this problem of attitude determination is a very rich one, and it's a big field of study. I want to go over a relatively simple algorithm for doing attitude determination that you might find useful. In particular, let's see, it is what's called the, where is it? The TRIAD method. Where is it? Yeah, so it's, I would say, the simplest version of attitude determination, where what you do is, say you have an accelerometer, right? And so say the accelerometer is just sitting on some device that's in some orientation. The reading out of that accelerometer, what it will tell you is the direction to the center of the Earth, right? It's going to read, even when things are sitting still, we're accelerating towards the center of the Earth, right? That's what gravity is. And the accelerometer will tell you that's the measurement that you will get out of an accelerometer that is just sitting on a table, the direction to the center of the Earth. So the vector that we know that, so what am I trying to say? In order to solve the attitude determination problem, you need at least 2 vectors that are known in the frame, the reference frame of the device that you're trying to determine its orientation, and that are known in the inertial frame that you care about. So maybe the inertial frame that we're trying to figure out the orientation of this thing is one where, you know, that's down, this is forward, that's right, that's left, right? So for me, in my reference frame, the direction to the center of the Earth is straight down. I have some device with an accelerometer on it that's at some orientation, and it measures for itself the direction to the center of the Earth being that way. It is kind of tilted like this, right? If you have 2 such vectors, and usually terrestrially, those 2 vectors are direction to the center of the Earth and direction to magnetic north, right? I know in this frame, perhaps that magnetic north is whichever direction it is. I think it's that way. Yeah. So I know north is that way. The device that I'm trying to determine, for which I'm trying to determine orientation, has a little magnetometer on it, and it, in its perspective, that way. Then those 2 pieces of information, the direction to the center of the Earth and the direction to magnetic north, are sufficient to figure out the 3D orientation of this object. And the simplest way of doing this is an algorithm called TRIAD, it's an acronym, I can't remember what it stands for, where the observation is, suppose we have, let's see, suppose we have three vectors that are known in the inertial frame and that are known in the reference frame of the object that we're doing attitude determination for. So maybe it's direction to the center of the Earth, magnetic north, and the direction to the sun. Okay, we know those three things in our frame, and then we measure those three things in the reference frame of the device. Then for each of those vectors, say V1 is the direction to the center of the Earth, V2 is magnetic north, V3 is the direction of the sun. And the little n superscript indicates my frame, the inertial frame. And in order to rotate each of the measured vectors to each of those things to our frame, there's some rotation matrix that we'll call Q. And the superscript there means a rotation matrix that takes us from the body frame, the frame of the thing, to our inertial frame. And it's the same for all three of these because the sensors are all rigidly attached to the same thing. They all have the same orientation. The observation is, well, that's true, right? For each of these vectors, there's some rotation matrix that rotates our measured vector to the known inertial vector. It's the same vector, it's just measured in different frames. We can stack those into a matrix and we say, okay, all three of those vectors in our frame is equal to, so that's a 3x3 matrix, right? All three of those vectors in our frame is equal to that 3x3 rotation matrix multiplied by those three same vectors in the measured frame. And then in order, what we actually care to solve for, what solving the attitude determination problem means is solving for that rotation matrix. And this becomes a simple matrix inverse, right? Simple mathematically, perhaps expensive computationally to do this matrix inverse. But what we do is we take our known inertial vectors and we matrix multiply by the inverse of those same vectors as measured by the device. And the output of this will be a 3x3 matrix that should be SO3, should be special orthogonal group 3. It's a rotation matrix. And that is our attitude, our orientation of the device. Now, I said you only need two vectors. Why do you only need two vectors? Well, say we only had V1 and V2. So say we had direction to the center of the Earth and we had direction to magnetic north. Then what we could do is we could do exactly the same thing that we just did up here. But instead of V1, V2, V3, we would look at V1, maybe that's direction to the center of the Earth. Instead of V2, we would do the cross product of V1 and V2. So that gives us another vector that is orthogonal to V1. And then instead of V3, we would do V1 cross with the cross product of V1 and V2, which gives us a third vector that's orthogonal to this first two. Why can't we do what? Why can't we take the part of V2 that's orthogonal to V1 for the last element? So we're building from two vectors, we're building three vectors that are all mutually orthogonal, that span R3 and are mutually orthogonal. And we're doing so in a way that from those two vectors, we build up three vectors that are all exactly orthogonal to one another, which guarantees that this is invertible. They don't have to be. They don't have to be. I may be in some orientation where north is that way and the direction of the center of the Earth is, quite close to it. Right? And even in the case where those two vectors happen to be relatively near to one another, the accuracy decreases, but this allows for us to still solve the problem. This suggests too, by the way, that if you know one of these vectors better than the other one, if you know V1 better than V2, your sensor's better, then you want to be a little bit careful about, which one do you use in this element, which this one appears in every one of these calculations, right? So whichever the most accurate measurement is, that's probably the one that you want to use for V1. But then, you get an accelerometer and a magnetometer, which often, by the way, come on the same device. These 6 degree of freedom, often I2C or SPI devices. You read off the accelerometer, you read off the magnetometer, run this algorithm, and then you could render that thing in 3D space in the correct orientation. Make sense? Okay. Something else I'll write about, something else I'll talk about is a lot of people are doing synthesizer-y type things. And I want to point you to, on the course website, there's a page called, down here, probably an application, sound synthesis. Some other interesting stuff down here too that you might be interested in, but sound synthesis. And in particular, I'll point you to two things. One is FM sound synthesis. This allows for you to, using a direct digital synthesis synthesizer. In lab one, we were producing pure frequencies, right? Pure tones. We were modulating those frequencies, but it was pure frequencies. What we do here is we produce a pure tone and then modulate it with another frequency according to the rules specified here. And what this provides for you is a series of degrees of freedom, knobs that you can turn, that will produce a sound with the fundamental frequency that you desire, but warped in interesting ways. And you play with these a little bit, and you'll get sounds that sound a lot like a string or a lot like a drum. These make sounds. That's kind of string-like. It's not doing any physical, it's not modeling any physics of the string. It's just producing sounds that happen to sound like strings. Here's something that sounds kind of like a drum. Right? Struck string. You get an FM synthesizer built, and I promise you will twiddle with this for hours because it's just interesting to hear what comes out. Oh, that downloaded something. Okay. The other algorithm I'll point you to is the Karplus Strong algorithm, which creates quite realistic string noises, which for those of you that are maybe simulating guitars or something, you might be interested in this algorithm. Let's see, here's a plucked noise. So the point being, if you're building a synthesizer and you want to synthesize stringed instruments, there are lots of options available for you to do that. Or, you play with these FM parameters a little bit and it stops sounding like stringed instruments and starts sounding like sci-fi laser gun sorts of things. The other thing I'll just point out, because I've had a few questions about this, is in lab one, we used a direct digital synthesis synthesizer to produce one tone. If you wanted to produce a chord or produce two frequencies simultaneously, you could have two direct digital synthesizers producing two different frequencies. You would add those two together in software and send the sum to the DAC. And what will come out is the superposition of the two frequencies. So you can instantiate a bunch of DDS synthesizers in software, sum together and send them to the DAC. And what you'll hear is the frequency of all of those synthesizers simultaneously. This was in a previous semester for lab one, the sound synthesis lab we did. You know how phones, when you push the different, there's specific tones associated with each. Those are all very well documented what those tones are. Turns out each of them is a combination of two pure frequencies. There's a unique pair for each dial tone. And the project in previous semesters was to take that keypad and simulate all of the tones for each of the phone button presses. I think the birds is a little more fun, but that one's fun too. Okay. Any questions about these things? What else might you be interested in? Let's see. Bruce has a page here on neural modeling neurons and such that you might find interesting. Yeah, and then the other page I'll point you to that hopefully all of you have found is the final projects page. People have found this, right? Which allows for you to look back at every final project that's been done in this class all the way back to like 1999. Back when this whole class was in assembler. So lots of resources here. And some of you have made the observation that your proposed project is quite similar to one that's been done previously. That's okay. And you should feel okay looking at that stuff as a resource. That's fine. Clearly you can't copy it, right? But if you want to use it as a resource, that's really fine. Okay. What else do people want to hear about? We're about out of time today. Next week on Monday, is there anything that people want to hear about? We could talk about the same things again. If people want to go over DMA again, we can talk about that. We can talk about, we can not talk at all. We can just do more lab time starting on Monday. That's fine too. We can go over, there's a relatively large number of people doing interesting mathematical things. If you want to have a lecture on like the Mandelbrot set, we could do that. People would find that relevant. If you want to hear about chipsats, the little satellites, those are microcontroller-y. We could talk about that if you want. Or like I said, we can just plan to be in lab and we'll wrap up lab 3 and start rolling on final projects. Let's meet again on Monday. We'll meet again on Monday and touch base, and then maybe starting on Wednesday, we'll go to full lab sections, but we'll meet again on Monday. In the meantime, if you want to talk about something, let me know in lab or send me an email or something. And otherwise, I'm just going to guess at what people would like to hear about.